Thank you. So my name is Alexander Lyubartsev, and I'm from Stockholm University, and I'm one of modeling partners within this project. So in my presentation, I will talk about statistical and physics-based modeling, which are an important part of the project. So just remind you that our SmartNanoTox project is financed within Horizon NMP 29 call, which is called Increasing the Capacity to Perform Nano-Safety Assessment, and particular aims of the program. Among the aims are to develop and demonstrate the mechanism-based understanding of toxicity, also to link potential for adverse effects to specific physical or chemical properties on nanoscale. And it is clear that for addressing these goals, just modeling and simulation are the tools which is relevant to use. And that is why modeling is an important part of our project. So if you look at the situation with modeling of toxicity for a few years ago, then it was mostly what is called statistical type of modeling, that is CUSAR type of modeling. These are statistically derived relationship between properties of nanoparticles and non-adverse outcome. So as the input in the statistical method, we have a number of nanomaterial descriptors, such as the size, as distribution, shape, surface coating, charge, maybe Z potential, band gap, and so on. Different experimentally measurable properties of the nanomaterials. And we try to link these descriptors with some adverse outcome or just with biological effects which can be observed in vivo and in vitro experiment when the organism are subjected by the action of nanoparticles. And statistical model, we use statistical models to try to link this data using different methods, from simple regression. We can use neural networks, machine learning, artificial intelligence. And this in principle gives us the way of evaluation or prediction when the model is developed. We can work rather fast if we put input data, then obtain result. The problem with the statistical approach that in many cases data, and especially reliable data are not enough. It might be also difficult to find correlation between input parameters and outcomes, because here we have a very long chain of events from starting contacts of nanomaterial with the organism and to adverse outcomes. And essentially, statistical models do not provide information about mechanism, how it is going on the whole way. And especially problem can come if we have new materials for which data are absent. So, and that is why mechanism-aware approaches are very much wanted. And physical-based modeling is just a way to provide insight into mechanism. Because physical-based modeling, modeling which is based on physical laws, which can be from on the very fundamental level. These are laws of quantum mechanics. They are called ab initio approaches when we deal with atoms consisting of nuclei and electrons, and essentially we solve Schrödinger equation for the electrons in order to model the small piece of materials. On a larger scale, we use classical modeling, employing classical representation of atoms, which moves according to Newtonian laws of motion. And we can go further to coarse-grain level of modeling when we study molecular assemblies. In all cases, rules of the game are physical laws, that is either quantum or classical, and also statistical thermodynamics. And such modeling gives us possibility to have a direct insight into what's happening, to follow all the sections events on the molecular level. But of course, problem that by doing this molecular type of modeling, it is very difficult to come to prediction on the level of the organism. When you do molecular modeling, we can in fact link different modeling levels into a chain of models, and this is called multiscale modeling. This allows us to fill the gap between atomistic size and largest size. This is example how we do multiscale modeling of nanoparticles corona composition. We did all the whole chain of these models, starting from ab initio modeling of titanium oxide surface, considered reactivity and the formation of hydration pattern. Then we use this information to study interactions of individual amino acids with titanium surface using data on the structure of titanium surface and also hydroxylation and also for seal parameters. Then we use the data obtained for individual amino acids to parameterize coarse-grained model, and then we can predict how proteins will interact with nanomaterial, and then go to even more coarse-grained model when you consider many proteins and how they form protein corona. So all this chain of events can be done in physical-based modeling. But still, even this level is very much far from what we want to do, is to predict adverse outcomes on the level of the organism. And so here we do some kind of handshaking of molecular modeling and system biology, that we use the concepts of adverse outcome pathways, which are well now also developed within the SmartNanoTox project. And so within adverse outcome pathway, the idea that we have a molecular initiating event, is some event on molecular level when nanoparticle meet biomatter, and it calls some sequence of events which go further to organelle level, cellular level, tissue level, and so on up to some adverse outcomes. And what we can do in molecular simulation, we can go from nanomaterial properties to describe these molecular initiating events, because these are events happening on molecular level. And such effect example of such events, it can be corona formation, can be membrane wrapping or membrane permeation of nanoparticles, or maybe sensing of receptor, sensing of nanoparticle by receptors. So these are all examples of possible molecular initiating events. And so this connection gives in principle fully mechanistic description of toxicity. But of course, this is computationally expensive, because it's still is a very long computation to model all the way up to events which we call molecular initiating events. So for the idea in the SmartNanoTox project is to combine statistical and physical-based modeling, that we use physical-based modeling in order to formulate QSAR connecting nanomaterial properties and molecular shading event. And here, so we here combine statistical and physical-based modeling, which allow us to utilize advantages of each. And examples of action which we do is that physical-based modeling, like molecular dynamics, can provide new relevant descriptors which can have high predicting power. And in principle, we go from descriptors characterizing the nanomaterial itself to descriptors characterizing interaction of nanomaterial with biological molecules. And also, physically based modeling can be used for training of statistical models like machine learning and artificial algorithms, which link computed physical chemical descriptors and molecular initiating events. And so that's like a QSAR, we call QSAR, which built on this principle is iQSAR, that is QSAR which is aware of molecular interactions. So the example of advanced descriptor is characterized by nanoreaction is binding free energies of biomolecules to nanoparticles. So when we are talking about traditional QSAR, that it uses conventional descriptors such as size distribution of nanoparticles, their shape, surface charge, and so on. The question can be, however, how to characterize a material quantitatively. that we deal with nanoparticles of very different origin, with metal oxide, metals, carbon materials, advanced ceramic, and so on. So how to compare them is like comparison of apple and oranges. So that's why we propose used absorption-free energy as a kind of parameters which characterize interactions of nanomaterial with biomolecule. So why then? Like I say that binding free energy, the free energy itself is a fundamental physical property which describes direction of change of all transformations. It is strictly defined theoretically and also measurable experimentally. According to this relationship, it's not easy, but at least a direct measurement can be done. It's just ratio of concentration of absorbed molecule in bound in a free state. It also expresses strengths of interaction of biomolecules to the material. The lower, more negative free energy, the stronger is binding. And also it's directly relevant to phenomena such as corona formation and membrane permeation and other events. So as a set of biomolecules for which we compute absorption-free energy, we selected a set of about 30 parts of components of biomolecules. And these are amino acids side chain analogs that for all naturally occurring amino acids. And we took analogs because to remove backbone part, which is common for all and which may give some redundancy of data. But we use glycine and proline with a backbone fragment to represent the backbone of proteins. Also, we compute binding energy for protonated or deprotonated form for some amino acids which can change protonation form in the range of pH close to physiological. And also we compute this for fragments of lipid heads and also for glucose as component of sugars. So totally we have about 30 binding free energy descriptors, and we can compute these for different materials. And here you see that absorption free energies for binding to rutile 100 surface, that all positive values means that these biomolecules do not bind to titanium and only a few polar molecules can bind to it. For carbon nanotubes, we have mostly negative free energy, which shows strong binding, especially strong for aromatic amino acids, which have sense. And you see that this approach allows to compare on equal footing different materials and how they see the biological matter. That it's kind of fingerprint of materials in the biological media. So this graph also shows binding free energy for carbon nanotube with different functionalization. So functionalization also change binding. And further we accumulate this data and then we can try to build, we already did some test studies of building neural networks which connect absorption data and biological responses. And here is the example of results from neural network which trained by data on inflammation, that is neutrophil influx into lungs of mouse after inhalation. And this was done for a range of materials in the SmartNanoTox project. And you see a nice correlation that between predicted and experimental results for the change in neutrophil influx. So it shows that these descriptors have a predictive power. So we collect all the results on absorption-free energy. We did computations for a number of materials: titanium, silica oxide, iron oxide, different carbon nanotubes called graphene, and we collect all results into a database of bio-nano interactions. Not only just absorption free energies, but also potential of mean force, which express free energy on a certain distance from the nanomaterial. And also this potential of mean force are used to model as effective potential in square-root models, which allows us to compute absorption energy for proteins and absorption energy for a big number of proteins. The number of surfaces were also computed and also accumulated in the database. And I said it will be publicly released after end of the project. And we will continue this the population of the database with this data further within the NanoSolve project, which also provide tools for nanoinformatic analysis. And finally, I already mentioned that physically based modeling can be used not only as generation of new types of descriptors, but also we can directly model certain type of K-events. And here is some preliminary results for modeling of such molecular initiating event, like sensing of nanoparticle by tool-like receptor. So these receptors are responsible for recognizing of some microbial components, LPS, and if this is a part of the immune defense system, that interaction with LPS activate these receptors and to switch on the immune response. And the question is whether nanoparticles can induce a similar response. And for this, we carried out molecular dynamics simulations of LR receptors in membrane as well as its interaction with some of nanoparticles. These are examples of such simulation. For interaction in nanoparticles, actually use only extracellular domain of TLR, and this is the interaction, how it can be done, how it can be seen for titanium oxide may come, but it do not affect any way TLR structure, and the free energy profile is fully repulsive. That's why it just do not interact with the TLR. For carbon nanotubes, we have such binding configuration, and if you look on the PMF profile, we see that there is a minimum, but it seems that it separated from other state by a barrier to come to this configuration. And for graphene oxide, we get strong attraction, and it seems that even this need to be analyzed further, that it is done, that it is bind to this part of the protein. So I see that this different nanomaterial interact differently with receptors, and some conclusion can be done on whether a specific nanomaterial can activate receptor. So finally, conclusions from our take-home messages as that physics-based simulation, they provide useful insight into biomolecular nanomaterial interaction, and that contribute to mechanism-based understanding of toxicity. And this modeling can produce relevant descriptors to statistical models with potential to improve predictability and facilitate grouping across methods for prediction of toxicity. And particularly, we introduced new type of descriptors and computed them, descriptors based on binding free energies, which can characterize different types of nanomaterials on equal footing. We also demonstrated possibility to directly model molecular initiating events of specific other cell compounds by the simulation.